Hello, my name is Benjamin Selinger, and welcome to my SURF presentation. I'm doing the AI-driven insights of the strategic optimization and sustainable evolution of modern building energy systems. So that is basically the importance of using these new AI systems to help us more easily compute and understand the energy system of our home. So that being how heat comes into our home and how heat leaves our home through multiple means, such as sunlight coming in or AC going out. And in the past, it would be very hard to look at all of these things together and sort of analyze what would be the best um, design practices, I guess, to build your building. But now with these new modern AI-driven software, we can kind of compile everything that we need into one system, and that can tell us the best orientation for certain things like solar panels and walls, windows, even trees, and how shade can affect certain buildings. Um, it is inconceivably complex to capture how energy flows through a system that constantly is being influenced by changing environmental and operational conditions. Solar radiation comes from both daily and seasonal direction, affecting the potential energy generation from solar panels. At the same time, building energy demand, particularly for cooling functions, with temperatures occupying and using patterns accordingly representing the interaction factors requires more than static assumptions, as real world performance depends on dynamic and interconnected variables. To address this, detailed models can be developed to represent yearly and daily patterns of solar radiation and estimate corresponding solar panel power output. Alongside this, energy consumption patterns, such as air conditioning usage, can be approximated based on thermal loads. With the building, the insulative properties of the structure, determined by materials, construction methods, and window performance, play a critical role in regulating heat transfer and therefore influence overall energy demand. In addition, location-based parameters must be considered, including geographic positions, local climate conditions, and environmental elements such as nearby buildings, vegetation, and shading, all of which impact both energy generation and loss. My key design parameters include temporal resolution of the modules, accuracy of environmental data inputs, solar panel characteristics, thermal properties of building materials, and consumption of occupancy and system usage. By incorporating these factors into a cohesive analytical framework, a more realistic representation of building energy systems can be achieved, allowing for improved evaluation of efficiency and performance under varying conditions. Building on these findings, the integration of advanced computational techniques, particularly in artificial intelligence, reinforcement learning, provides a pathway to move beyond purely perspective models towards adaptive and perceiving productive energy management systems. Recent literature indicates that reinforcement learning based control of building energy systems can reduce total energy consumption by about 8 to 30%. Depending on climate systems, complexity, and the level of integration between renewable generation and demand management in optimized cases, especially when paired with solar and HVAC control, peak load reductions of 10 to 25% and improvements in self-consumption in solar energy by 15 to 40% have also been reported. Transcending these perceptions into real-world context, a typical family home in Hawaii consumes roughly 500 to 700 kilowatt hours per month, with electrical costs averaging about half a dollar per year per kilowatt, among the highest in the United States. This corresponds to a monthly bill of approximately $175 to $315. Applying an energy savings of roughly 8 to 30%, you could expect a savings of up to $100 per month, or about $1,000 annually. Depending on your system performance and user behavior, homes with integrated solar and intelligent control systems may achieve even higher savings, by reducing reliance on grid electricity during mid-peak pricing. Beyond individual households, the broader adoption of these technologies at scale has significant implications for building design and energy policies. When implemented correctly, through updated building codes, smart grid integration, and sustained energy management systems, these approaches can shift buildings from passive energy consumers to active participants in energy networks. Engineering research highlights the distinct communities using coordinated intelligent control can achieve aggregate energy reductions exceeding 20%, while also improving grid stability and reducing infrastructure strain. As a result, the growing momentum towards incorporating adaptive energy management systems such as Aladdin into new building standards. This includes requiring for high performance insulation, solar readiness, real time monitoring systems, and AI driven control frameworks. By embedding these technologies into consumption reinforcing practices, future buildings can be designed for not only efficiency but under static assumptions for continuous optimization, in response to real world variability, ultimately supporting more resilient, cost effective, and sustainable energy systems to both individual and societal levels. Thank you for listening.